Okay, so good evening, and we'll start this live session. So today's live session topic will be on based on the root locus. So we'll solve some some basic problem on root locus. So this week first content of the NPTEL lecture video. So as you already have gone through this content of this week 5. So the root locus. So as you already know that the poles or the roots of the closed loop system, that is the auxiliary root, that is in the equation that is present in the denominator. So we call them as poles of this system, closed loop system. So they are important in terms of if you want to know like various system behaviors like transient, steady state error, and so on. So they are very important to us, and you want to know their location, right? This is pole location, but it may be possible that some parameters may be variable in the system. For example, the gain, as you consider, if it is variable, then you know that characteristic equation will change, and so the pole's location will also change. So root locus is a technique where you find this closed loop pole location as the system parameter actually changes. So initially we just consider this system parameter as the gain. So in short, if the gain varies, how this closed loop pole locations are varying. Okay, so in negative feedback system, the gain should be positive, right? So you vary this gain from 0 to infinity and see how this location of the closed loop poles actually varies with the this gain. So that will actually give you some insight, if your gain is also a region parameter and you want to place your poles in certain location, then it will give you some insight how to put this gain. And also it's if there are some parameter that are variable and you know like how this parameter varies, then your closed loop pole locations are how these closed loop poles are located. So for example, they can, if you basic need will be like system stability, then you need them and the location of the poles to be in the left hand plane. So around what up to what gain these poles are located in this left hand plane, and so on, you can find this, right? So let's discuss some problem first. So okay, so first problem, as you can see, so it's just some statements are given regarding the root locus. So and you have to consider like what statements are actually false. Okay, so first statement is root locus starts from 0 and ends at the pole. Second is like it is symmetrical about imaginary axis. Okay, so number of asymptotes of the root locus equal to the difference between number of poles and 0, and root locus gives the locus of the closed loop poles if the open loop gain is varied from 0 to infinity. So all are basic properties of root locus. So you have to see, okay, which statements are actually false. Okay, so you can answer through poll. Okay, so then we will discuss about this. Okay, so maybe we can discuss this. Okay, so so let's just analyze this root locus. Okay, so this closed loop poles are given by this equation, right? So the denominator part you make it equal to 0 and you find this closed loop poles. Okay, so let the GH be written as the numerator part and the denominator part like this. Okay, so and this gain. Okay, just separating that gain of that. So then 1 plus GH equal to 0, that will give you this characteristic equation or the closed loop poles. So that can also be written as ns by ds, because I am taking this to be of this form, okay, equal to 0, or you have ds plus k into ns equal to 0. So you see that if k equal to 0, this term will there will be no term of the numerator, only we have ds equal to 0, and when k equal to infinity you can write this also like this also, ds 1 by k plus ns equal to 0, okay, for some k not 0, okay. So as k goes to infinity, you see that it will be ns equal to 0, okay, k goes to infinity, so it will be 0 first term, and we have ns equal to 0. So you see that when k equal to 0, your characteristic equation become from this ds equal to 0, and as k goes to infinity you have ns equal to 0 from this equation. As you can see, 1 by k will be 0, so ns equal to 0, and thus ds equal to 0 means from this you can see these are the open loop poles, right? ds equal to 0 and ns equal to 0 are the open loop 0. So root locus will start from open loop poles and it will end as k goes to infinity in the open loop 0. So the first statement says that root locus start from 0 and ends in poles of this open loop, so it is a false statement. Second one is root locus is symmetric about imaginary axis. So whenever you see that because your system should have like real coefficient, so your poles location or the 0 location, if they are like imaginary, then there should be a complex conjugate of each other. So that means they should be located symmetrically about the real axis, okay. So this is the real axis and this is the imaginary axis, and so when you vary this gain, so this location will shift but the symmetry will be maintained, right? So if there is some pole here, there should be some complex conjugate pole, so this symmetry, or for 0 also this is true. So but root locus is just plot of poles, so we just consider this poles location. So you see that this symmetry is maintained around the real axis. So if the root locus goes like this, then there will be also the symmetrical part around this real axis, okay. So but for imaginary part it may not be symmetric, that is it may be possible that root locus exists for left hand side, but there is no right hand side root locus, no branch of this exists in the right hand side of this imaginary axis. So it is symmetrical about the real axis, but it may be asymmetrical about the imaginary axis. So the second statement which says that it is symmetric about the imaginary axis is also false, okay. Then the number of asymptotes of the root locus is equal to the difference between the number of poles and zeros of the open loop transfer function. So if you recollect from basic property, so you know that root locus actually start from open loop poles and end in the open loop zeros, okay. And you also consider if the number of zeros are less than number of poles, then you also consider the zeros to be at the present at the infinity, because for s goes to infinity that will also make this transfer function 0, okay. So anyway, if you consider the zeros, you include this finite 0 as well as the zeros at the infinite, then you know that number of zeros equal to number of poles including all this finite and infinite zeros, okay. So you know that the difference between the finite poles and the finite zero, then there will be same number of branches that will extend to infinity, that will actually go to the zeros at the infinity. And so these are also called asymptotes. So asymptotes mean that as s goes to infinity, as k goes to infinity, that the gain goes to infinity, then you know that root locus will end in the the infinity 0. So they will be asymptote type, so their behavior will be similar as k goes to infinity around this infinity range, and these are the asymptotes, and you know that they are equal to the difference between the poles and 0. So because that is the number of branches of the root locus that will go to infinity. So third statement is actually true, okay. So you just go through basic properties of root locus. So these are this property, I am just explaining them. And root locus gives the locus of the closed loop poles as the open loop gain is varied from 0 to infinity. So this is also true, and this is true for, we are considering for only negative feedback system, okay. So this is true also for statement. So the false statement are only 1 and 2, okay. So this is 1A option, okay. So we move to the next question. So again, so basic question. So you have given a unity feedback, okay. So for feedback you will consider negative feedback, okay, always. So unity feedback, open loop transfer function is given, So the location of the centroid. Okay, so centroid is where your asymptote will meet. Okay, so again the basic question. So just try. Okay, if you have any doubt, you can ask regarding question also. Okay, so because these are very basic questions, so I'm assuming it's very clear. Okay. So question is clear, right? You know the centroid, right? So it is the point from which you draw the asymptotes. Okay. Okay, so let's discuss. Okay. So first you have to find this open loop. So you are given a unity feedback system with this open loop gain. Okay, so you have to find the open loop poles. Okay, then from this open loop poles and zeros also you can find the centroid, that is where these asymptotes will meet. Okay, so one question will be how many branches will be there in this root locus around this, that actually how many asymptotes, or I can say
Three,
huh?
three branches.
Three branches. Okay, just think about how many your open loop poles are there.
Open loop pools. Don't know, sir.
Okay, so this is open loop transfer function is given. Okay, so the open loop poles are, these poles are the the value of s that will make this gs equal to infinity, or in other words, the value of the s that will make this denominator equal to 0. Okay, so what is the degree of the polynomial that is present in the denominator?
180 degree.
No, I mean, I'm saying, okay, so what is the order of the equation in the denominator? If I write it, okay, I'm writing this equal to 0, the denominator term. Okay, so these are the roots, right, of this equation. That means the value of the s that will make this, this denominator term that is there, s into s plus 5 into this s square plus 6s plus 17.76 is there. So how many value of the s are possible that can make this equation equal to 0? So okay, so as you can see, there is a quadratic term is there, s square term is there, one s plus 5 is there, s equal to s is there. So let's just consider this equation first. Okay, so this is the equation, s square plus 6s plus 17.76. Okay, so we equal to 0. So this will give the poles of the gs, right? Is it clear? Yeah, I mean, how you determine this poles and 0? So for any uh, transfer function, okay, sorry, any just gain, okay, so just consider any equation gs, okay, equal to some ns by ds term. Okay, so you have some s equation in the numerator. Here it is only k. It could be also some terms like k into s plus z or something, s plus z2, z1, z2, like that also possible in the numerator, right? So I'm denoting it by ns, and the ds, which is this one, this term. So you know these poles are what?
Sir, which construction rule we applied here?
Which?
Which construction rules?
Okay, so construction rule, okay, I don't remember exactly this rule. So okay, I will talk about rule number. I don't know. Okay, I don't know sequence of rule number. This will be the rule where you, okay, so I'll just explain. Okay, so you just point out what rule is this is. Okay, so this is the centroid, means you have to find the location from which this asymptote will be drawn. Okay, so I don't know, this may be third or fourth rule, I don't know. Okay, so just I will just explain the rule also. Okay, so before that you have to like also consider what you want to find. Okay, so you have to find this open loop poles. Okay, so this is from this equation, right? This is equal to 0 is the, will give open loop poles. So for what value this can be 0? One value will be s equal to 0 will also 0, right? This equation, if I put s equal to 0 here, this will be 0, right? Whole term. So one solution is 0. Another will be s equal to minus 5. This term will be 0, right? If I put s equal to minus 5. And another will be this term, if this is also 0, that is s square plus 6s plus s square plus 6x plus 17.76 equal to 0. And this root will be, you can calculate is a complex conjugate root. Okay, so you can use calculator to calculate, or you can also use any other tool. So these roots are at minus 3 plus minus 2 j 2.96. okay, so these are two values, another value, another value. So there are four values for which this equation can be 0, right? So there are four poles, right? Is it clear? How many poles are there for this open loop transfer function, open loop gain? And how many zeros are there? Finite zero. You see that in the numerator, what is present in the numerator? Only k, right? So you cannot choose any s value for which it will be 0 unless k is 0. Okay, so yeah, so no finite zeros there. But if you consider like zeros at the infinite, then there are also 4 zeros will be present at the infinite, because for s equal to infinity, this denominator will also become infinity, and k by infinity will be 0. Okay, so your root locus rule says that you should start from open loop poles and end in the open loop zeros. So how many branches will be there? Because you have 4 finite poles, okay, for this open loop transfer function, and 4 poles, zeros are at the infinity, right? So how many asymptotes will be there? Yeah, right, 4 asymptote will be there, right? And you want to find like okay, so the 4 asymptotes. Okay, can anyone say what angle will be there for these asymptotes? Okay, we'll actually draw this root locus for this transfer function. Okay, so it will be clear. We'll go step by step. So first just consider the asymptotes of this. Okay, so how many asymptotes? You already told 4 asymptotes. And what should be the angle of this asymptotes? So you already know that this root locus will be symmetrical about this real axis, right? So how this asymptote should be present then? They should be also symmetrical about this real axis, right? So you can easily see that there should be like what angle should be there, or you can just apply the rule also. Okay, so I'm just writing this rule. So you have number of poles, okay, minus number of zeros. So I'm considering finite poles and finite zeros. Okay, so this you consider this number, and you let it be some number. Okay, k already there, so I'm just using it to be some, let a. Okay, so then plus minus 180 degree. So take the odd multiples of this angle and divide this number. Okay, so that will be the angle of this asymptote, right? So you see that the asymptotes could be angle what? So here this a is 4, right? Right. So if you divide by 180 by, okay, you take k equal to, first you can take 0, so it is plus minus 180 degree by 4. Okay, so what is this angle? One is 45 degree plus and one is minus 45 degree, right? Negative 45 degree. So okay, so we have to also find the centroid. So let's consider this is the centroid. Okay, we will find the centroid. So that's one asymptote will be what? At 45 degree angle, and another will be at minus 45 degree, this one. Okay, so how to find this centroid? Like you can draw this, right? Another will be, okay, just take the k value equal to 1, then we find that another will be this angle, right? 135 angle, this angle 135, this will be minus 135 degree. So you see that these are symmetrically located, right? These are asymptotes. The angle between them will be equally distributed, right? Is it clear? Okay, if you have doubt you can ask, okay, because this will be very crucial to understand, because okay, you can remember the rules, but it will be good to understand them, right? Why these rules are coming. Okay, so it's very nice if you can remember rules, but it will be good also understanding them. Okay, so anyway, this asymptote will start from one point, right? So that is actually called the centroid, right? So what is the value of the centroid? You can still apply this rule. Can anyone say the rule for this? Okay, so let's okay, so n number of poles and m number of finite zeros are there, then you take the difference and you take this number that is already there, a, right? The difference between the finite pole and finite zero. So this will give the value of the centroid. Okay, so you already know this angle of the asymptote, right? We already calculated this 45 minus 45, 135 degree and minus 135 degree. Okay, but we don't know from which point we should draw this asymptote, right? Because your root locus could start from, like, you can draw asymptote from here, you can draw from here also, right? So you have to find this point, exact point from which you want to draw this asymptote. In the real axis you have to find this exact point. Okay, so this is just simple summation of the pole minus summation of the zeros by the difference between them. Okay, so we are just considering finite poles and finite zero. So this pole, we already calculated this poles, right? So I have written this open loop poles. One is at a 0, one is at minus 5, and this is the complex conjugate pole. They are located at minus 3 plus minus j 2.96. Okay, you can just verify this. Okay, these are the poles. Okay, so you see that always this complex conjugate poles will cancel out, right? And zeros also, for there is no zero for this, but even if these zeros are present, they will be complex conjugate, so this imaginary part will always cancel out, and this their summation will be what? This exact term, like the second term 6. Is it clear? So without also calculating these poles, you can also find the, can you please forward this information to the concerned attorney? What information? Okay, solution 4 are not uploaded. Okay, I will try. Okay, I will tell them, okay, about this solution for assignment solution. Okay, okay, so okay, so so here, okay, so even, okay, you don't have to also calculate this exact pole. Okay, because this real part summation will be what? Yeah, this is right. Is it clear? Why this is actually? Because for this quadratic equation, the second term will be what? Summation of the pole. Last term will be the product of this pole, right? This is for the summation, because of this complex conjugate, this plus and minus will cancel out. So minus 3 plus minus 3 is minus 6. So minus of minus 6 is there, as you can see there, right? So for calculation purpose, you can also, you may, like for the centroid, you don't have to calculate the exact pole also. Okay. So okay, anyway, so we just use this formula and find this. So summation of the poles, as you can see, one is 0, 0, then one is minus 5, and two summation are minus 3, right? Okay, so and by a is 4, right? So it is minus 11 by 4, or it is what 11 by 4 2.75, right, minus 2.75. So this is the location of the centroid. Okay, is it clear or you have a doubt? Okay, I am doing all detail because we'll just plot this root locus for this also. Okay, so I'm just will proceed by calculating each of this term of this root locus. Okay, whatever you need property or this position of this root locus, so just you can plot them. Okay, so I'm assuming it is clear. Okay, so then we can move to the next question. Again the same transfer function is there, so you have to find the breakaway point. Okay, so just try, then we will discuss this. Okay, question 3. Okay, so if you have any doubt you can ask. Okay, because it will be good if you just have clarity on this. Okay, so you can answer the phone. Okay, so you know how to find this breakaway point, right? Zeros of xt okay, so the first question will be, what is the breakaway point? Can anyone say, answer this? What is the breakaway point? Okay, so that is the formula for calculating, but what is this breakaway point? Okay, so anyway we'll plot, and at the end also I will just discuss. Okay, after this question. So breakaway point means that, okay, so if your root locus is present between two poles. Okay, so first rule is what? First, from properties of root locus, you know that your root locus will start from open loop poles and it will end on the open loop zeros, including the infinite zeros. Okay, so if some root locus is present between two poles, that means there has to some point from which it will branch out, right? Because it cannot start at the open loop poles and end at the open loop poles. So there should be some branching from that will go to zeros, right? And it will end in the zeros. So that branching point is actually the breakaway point. And at the breakaway point, okay, so I'll explain like this. Okay, so let's consider for this. Okay, for this, what are these open loop poles? Can anyone say? We already calculated. One is at 0, one is at -5, other two at complex conjugate. We calculated -3, and it is plus j. We already calculated this 2.96. Okay, minus 2.96. Okay, I'll use the red. Okay, so these are the open loop poles, right? So first rule, another rule. Okay, I don't remember the rule number. So another rule, can anyone say like in the real axis, how to find this root locus part? Okay, so I'll just ask you. Okay, so from 0 to, this is positive part, right? 0 to infinity. Will there be any root locus in this region? Only for the real axis. Will there be any root locus? And the question is clear. Is there any part of this root locus there? Okay, so okay, anyway, this angle contribution, what will be the angle of any point on the root locus from this closed loop poles and zero summation? 180 degree, right? 180 degree or minus 180 degree, and it's odd multiples. So from that rule, if you just go through the lecture video, the rule will come like that if you have odd number of zeros or poles in only in the real axis we consider to the right, then that point will be on the root locus, right? So as you can see, at this point 0 to the right, this region is there, right? So how many poles are there to the right? The question is clear, right? From this 0 location, okay, this 0 pole here towards its right, how many poles are there? There is no pole, right? So 0, that is also even number, so there are no poles are there, so this part is not in the root locus, okay, this region, okay. And what about from minus 5 to 0? From this region, you see that one pole is there, right, at the 0. So this region will be, I'm denoting it like a green, okay. This region, this will be the part of the root locus, right? And what about this region beyond this 5, the left of 5? Will it be part of root locus? How many poles are there right to this region on the real axis? 2, right? So it will not be part of root locus. So you see that this green color only is a part of the real axis, that is on the root locus, right? Is it clear, or do we have to explain it again? Okay, so yeah, okay, so this is part of the root locus, and we already calculated the asymptotes, right? This angle 45 minus 135 minus 45 minus 135, and the centroid is at the point this minus 2.75, which is something between there, okay. So you draw this 45 angle degree, so I will use blue color, okay, 45 degree. So this is one asymptote, this is one asymptote, minus 45 minus 135 and plus 135, okay. And you see that another part of root locus will start from these two poles, right, these complex conjugate poles. So you have a part that is starting from one pole to another pole, right? So it will be like this will move like this, and this part will move like this, okay. But your root locus cannot start at this pole and end this pole, so that means it should branch out from this region and it will go through this asymptote, okay. Is it clear? Okay, so we don't know whether this will go like this or this will go like this, okay, and also symmetrically around lower half also, okay. We'll also see how it will go, we'll later calculate this first anyway. So you see that means you have to branch out this, your root locus will branch out from some point, and that point is called the breakaway point, okay. So okay, so let me draw it again, it will be clear. So what is happening, okay, I'm just drawing this real part, okay. This is from minus 5 and you have 0, right, yeah. So as the gain is increased, so this one part will be moving like this branch, another branch will be moving like, so at one point they will meet, okay, and they will branch out, okay. So how they branch out, like for example, let branch out like this and go, so we'll calculate that. But what is this property of this point when they break out? How many poles are there for closed loop system at that same point? So you see that, huh? Okay, so just see one root, okay, as we increase this gain value k, one will start from this pole location and another starting from this 0 location. Okay, so this part I am drawing here. So as the gain increase, this branch will go like this and this branch will go like this, so they will meet at one point. Okay, so this is breakaway point where they break away. You see that one pole is moving like this, another closed loop pole is moving like this. So at this point, how many poles will be there? Equal value 2, right? So one property of this breakaway point is that multiplicity of two poles exists there, right? That's how you take this derivative and make it equal to 0 and you get this solution. Okay, so if some question come like for what value of k, or you have like multiple poles are there with same value, right? So you can find this will be the breakaway point, or it can also be breaking point. Okay, so we'll consider also breaking point later. So breaking point means if there is a part between zeros, okay, instead of pole 0, also that means you have to go through some point and you then diverge there. Okay, so anyway, saying this, why I told this, because at this point, at this breakaway point, there will be two poles with the same value, right? So this is like same value, and this where the branching will occur from this. Okay, so to find this, as somebody has already pointed out, so this formula finding is very simple. So you take the dk by ds. So you first write k in terms of s, and then you take it derivative equal to 0 and you find this. Okay, so from this you see that 1 plus gs equal to 0 will give this closed loop poles. So this will be what we have 1 plus k by I can calculate here. Okay, so 1 plus gs, because hs is 1 here, equal to 0. So simplify that 1 plus k by this term 6x plus 17.76 equal to 0, or you can multiply this and plus k. So it will be, numerator term will be what? This one, and the denominator will be this term, right? I am not writing this, equal to 0. This means this numerator part should be 0. Okay, plus k is there, plus k equal to 0, right? So the numerator part, from this numerator part you have s plus 5, this part I am writing here, s square plus 6x plus 17.76 plus k equal to 0, or k equal to negative of this. Okay, I can write k equal to negative of this. Okay, then you take, just simplify this and take the derivative. Okay, just multiply this, so it will be what? S square plus 5s times s square plus 6s plus 17.76. So it will be s4 6s cube 17.76 s square. Then where this I am multiplying with all this term, so here 5 s cube 30 s square plus 5 into 17.76. Okay, so it is 5 into 17.76, which is 88.8 s with 0. So you just add this term, so you get s4 plus 11 s cube plus 30, sorry, 30 plus 17, so 47.76 s square plus 88.8 s equal to 0. Okay, not 0, I am just calculating this. So this is negative of this equal to, okay, because this term, so negative of this equal to k. So you take this derivative dk by ds equal to 0. So this is equal to minus k, right? So from that you see that the derivative of this will be what? 4s cube. Okay, I am writing the derivative of this term. Okay, negative of this, so you can negative also put minus in. Then we have 33 s square plus 47.76 into 2, right? So it is 47.76 into 2, which is 95.52 s plus 88.8. Okay, this is equal to 0, right? So this is third order equation, so we can use a calculator to calculate this. Okay, so just assume that you somehow calculate this, so you can use calculator, scientific calculator, to calculate this. So the roots are from this. Okay, so I already have calculated them. So this is minus 1.83, one is, and because it is third order, so 3 root will be there, and another 2 are complex conjugate, minus 3.21 plus minus j 1.35. Okay, so then you can verify which of this value actually lies in the root locus. Okay, so for example this minus 1.83. Okay, so minus 1.83 will be some point there, right? There, and you see that it is over this root locus, right? So that is actually one breakaway point. Other are complex conjugate. You also have to verify for complex conjugate, but you can see that for this complex conjugate, if you put this value here, you will get k also imaginary. Okay, not real. So these are not actual breakaway point. So only this point is minus 1.83 is the breakaway point. Okay, this one. Okay, so is it clear? Okay, just simple calculation, because if you know the formula you can calculate. Just I am explaining that little bit more. Okay, okay, so if it is clear, then we move to next question. So again the same transfer function is given, so you have to find like for what value of the gain the root locus will cross the imaginary axis. Okay, so how can you find? Can anyone say? So this is question 4. Okay, so try this question. Okay, so we'll discuss again. So you can answer through the poll. Okay. Okay. So what should you apply to find this? So if you remember, you can apply Raoult-Horich table, right? Because it will give like for what value it will cross this imaginary axis, right? And because after crossing this imaginary axis, it will go to the right hand plane and it will become unstable. Okay. Okay, is it clear, or like how to find this? Okay, so okay, maybe I can explain this. Okay, so you know, like from this open loop gain, this GS, you can find this closed loop poles, right? For what value of k it will cross this imaginary axis, right? Or whether the system is stable or not. That will be using that Raoult-Horich criteria, right? So we'll use that same technique to find this at what point it will cross this imaginary axis. So as you can, if you remember from this Raoult-Horich criteria, okay, so when this imaginary poles happen, okay, so you remember this Raoult-Horich table, right? So when imaginary pole can happen, whenever a row becomes 0, right? You remember the Raoult-Horich criteria, right? If a row becomes 0, then it is possible that
Yes, sir. We know when the sign changes.
Yeah, the sign changes, that means you have unstable pole. But when this row becomes 0, you have this imaginary axis pole can happen, right? A row completely becomes 0. So we'll use this property only. Okay. So first you write this. Okay, for this value of the k, okay, so you write this transfer function. Okay, so we already have written this closed loop the characteristic equation here, this one, right? This one plus k is there because this is equal to minus k, so we will write this again here. Okay, so I write this s4 plus, I'm just writing this one, okay, this term plus k because that is the closed loop equation. Okay, so it is s square plus 88.8 s plus k, right? So now you just apply the Rouse-Hodge table. Okay, so s4, s3, s2, s1, s0, this is 1, this is 47.76, this is k, then you have for this is 11, this is 88.8. okay, then you just complete this Rouse-Hodge table. So first one will be this multiply this minus this multiply with this by divided by this, so which is 11 into 47.76 minus 88.8 by 11. Okay, so I'll just calculate this, so which is 11 into 47.76 minus 88.8 by 11, so it is around 39 point something, so 39.69, and the second term will be this into this minus 0 by 11, so it is just k. Okay, so let's write it clearly. Okay, so this is s3, this is s2, then s1 and s3. Okay, then s1 will be what? 39, this one into this term minus k into this 11, so it is 39.69 into 88.8 minus 11k by 39.69. okay, and last one will be just k. Okay, this row, okay, this is s0 k. Okay, so to make one row 0 you have this choice right here, this green box, you can make it 0 because k is already greater than 0. So this is, you see that whenever a complete row becomes 0 you can have imaginary axis pole. So if you make this 0, so it has only one element in S1. So if it is 0, then you see that this auxiliary polynomial will be given by the row before that, and you can have imaginary axis pole. It is possible for that. So for what value k possible? So this is equal to 0. That means you have to make 39. Okay, I am writing this 39.69 into 88.8 minus 11k should be equal to 0, this numerator part, because denominator is positive term. So k equal to, just here 39.64 into 88.8 by 11. I just calculate this, 39.64 8.8 by 11, so it is around 320. okay, 320 point something, so this one, okay, around that, this numerical sum you have to use that. Okay, so for that value of k, you see that this row will be 0, right, this green color. So you can have an imaginary axis pole. And what is this value of this like imaginary point where this it will cross? You can find it from the auxiliary equation, right? So what is the auxiliary equation for that? This will give the auxiliary equation, right? Which is 39.39, so 36 and 18. Okay, 39.69 s square, because this is the coefficient of this one, plus k equal to 0, and k value we already calculated it, 320.4. okay, so 320.4 equal to 0. So s value will be what? Let's solve this. So it is 320 by 49.69 square root, right? So it is 2 point something, so plus minus j 2.84. okay, so at this point it will cross this imaginary axis. Okay, is it clear? Okay, so if something is not clear, just ask, I will explain. Okay.
Sir, like why did we equate it to zero, sir, of the s to the power of one stage?
Okay, yeah. So you remember Raoult-Horowitz criteria, right? This table.
Yes, sir. Like we used to have, if there's one of the point is minus, we consider it to be unstable.
Yeah.
That's the only point.
Yeah. So there was also another point, right? So when a complete row becomes zero, what you do? You remember that point, right? Also, there is some cases where a row can be also zero, right? All element in a row can be zero, right? So then what you do? You take the derivative of the row just before it, and then you continue this Raoult-Horowitz table, right? Okay.
Yes, sir. Like, can you explain that concept a bit,
okay,
sir? Like,
okay,
can you
so
give
I
an
will
introduction of
explain,
it?
So I will omit this and explain here. Okay. So I'll briefly explain this. Okay, you can go again and see that. Okay, so what happened? Okay, so you have some that m like this, m minus 1 and m minus 2 and so on. You have this Raoult-Horowitz table. So it is possible that a row can happen with all zeros. Okay, all elements can be zero there. So you already have seen this. So and that happen only in the odd power of s. Okay, so in this case, in our case it is s1. Okay, I just omitted that. So it always happen in the odd power, and what you do, you take this derivative of this above this row. Okay, so this is s minus 1 means it will start from s minus 1. So let a element is b, c and so on. So you write this auxiliary polynomial using this coefficient, which this is the highest power, and you skip 1 by 1. So it is a even number power will happen. Okay, so then you continue all this row using the derivative of this term. So this is this rule you already know. So what is this property of this zero? So whenever a complete row becomes zero there, so then it is possible that you can have like symmetrically located roots. Okay, so symmetrically located poles for this system. So that means if there is some pole here like this, so you know this is complex conjugate pole will be like this, but the property will be that it is also symmetrically located with this imaginary axis. So it will be like this. Okay, if it is present in the real axis, then there will be some also pole. Okay, so to briefly say, whenever a row becomes zero, you have this possibility that this root will be symmetrically located above this imaginary axis. Okay, so if a pole is located here, then another pole should be located symmetrically about this imaginary axis. Okay, so if pole is here, you already know that complex conjugate pole will be there, right? But for this case, you also have this symmetrically located poles like this. Okay, so that means it is also possible that, for example, if some pole is there like this, it is also possible like this also. Imaginary axis pole possible only in this case. Okay, so you just go through this Raoult-Horowitz criteria table. So only when it becomes zero, a complete row, then only it's possible that you can have this imaginary axis pole. Okay, so like to briefly say, whenever a row becomes zero, then only it is possible that you can have imaginary axis poles. Okay, is it clear?
And if it is not zero, then there is no imaginary imaginary axis pole.
Yeah, that is not possible. Okay, if a row is not zero, completely zero, then it is not possible that
Only on the real axis.
No, it can have in the real axis, or it can also have like this 0 point also. Okay, yeah.
Okay, sir.
Yeah, but not in the imaginary axis, it is not possible. Okay, so only possibility is only when a row is completely zero. Okay, so if it is, the row is consist of one element, then just that element will be zero. But if it is consist of more than one element, then every element should be zero. Okay, So that is the property of the Raut-Harish table. Okay, so to find this, like here we have a gain, right? K value is variable here, so you have to find like what value of the K. This equation will have imaginary axis poles, right? So it will the point where this root locus will cross. Like if it is crossing this imaginary axis, that means it should cross some point, right? Like this. So that means at that value of the K, it should have poles at this imaginary axis. So that value of the gain, how to find this? So because this K is actually unknown to us at first point, so we will see like what value of the K can make this a row to 0, right? So for this case, okay, let's just write this table again so it will be clear. So we have this characteristic equation, this is the characteristic equation, okay. So we don't know the value of the K beforehand, we want to find a value of K for which this imaginary axis pole will be located, okay. So we write this table, so it is S4, S3, S2, S1, S0. So the table I'll just write it. So this is 47.76, then K 11. I'm just repeating it, so I'm just directly writing. Okay, you know how to calculate this. So this value was like 39.687. This is K, and this value was 39.687 into 88.8 minus K by 11, and last value was K. Okay, so you see that always look for the odd number. Okay, odd number S power whenever odd, because whenever you have this kind of auxiliary polynomial, that will be even number. So just below that you have row of 0, so that will only possible at the odd number of table, like this. You see that at this point only one element is there, right? So if this is 0, then it is possible that you can have imaginary poles, right? Imaginary axis poles. Is it clear?
Yes, sir.
So for what value of K it will be 0, that's the numerator part, we make it equal to 0, right? And solve this K value, where you get this. So this is 9, I think. Okay, so for K value of this, K equal to this term, okay, sorry, this is 11K, because this is multiplied with this is 11K, okay, this multiplied with this, okay. So K value this term by 11, because you are making this equal to 0, that means K equal to what? 39.687 into 88.8 by 11. So this is what you will get this after calculating. So for this value of K, you see that this will be 0, the numerator, the whole term will be 0, and you know this auxiliary polynomial will be what? How to find this auxiliary polynomial? You remember from this Raut-Harish criteria, right? How to find this auxiliary polynomial? It will be the coefficient just, can you anyone answer? It will be
That's
just
1 square plus
this will be the auxiliary polynomial just before this 0. So once you take this K value to be this 324, this term will be 0. So just before it you find this auxiliary polynomial, that will always be a even number polynomial. So it will start from S square. So you have 39.687 S square, this one, so I am just using 39.69, okay, rounding up, plus K term, this one K value you already calculated this, so you solve this, so this will give this imaginary value where these poles are located, and that is exactly the point where this root locus is crossing this J omega axis, right? Is it clear? Or okay, you go through this lecture video again very carefully, and still you have doubt, you can ask, okay. So to just summarize what you do, so you look for imaginary axis pole, you need a row of 0, right? And this row of 0 can happen only in the odd number of power of S, okay. So if you have a variable parameter, like here you have K, so if you can choose and make this a complete a complete row is 0, then you can have a imaginary axis pole, right? So here you see that in the S1 row you can choose k value and make it 0. So for that k value, you see that you can have imaginary axis pole, and that auxiliary polynomial will be given by just before this, the row before present above that S1 row, right? So it will always be even number polynomial, and this polynomial, from this you can calculate the value of the poles there. Okay, so this is also gives this what? So you remember undamped system, where you don't have any real part, right? There is no damping is present. So your poles are just imaginary poles. So you see that at this point, s equal to this point, the real part is 0, and this is just your system is undamped, right? There is no damping is present. The damping is only present only when you have a negative real part, right? Okay, you can also look for that also. So this will give the, what is the natural frequency then? This is the natural frequency, right? This term, you see this imaginary axis poles here crossing. Okay, you can also check this. Okay, you know this undamped system, the frequency at which it will oscillate, right, when the damping is 0. Okay, so then next question is like angle of departure. Okay, so until now what we have seen, so we have the same system again. So we have a pole at this 0, we have a pole at -5. From this equation you see that one pole is at 0 and at -5, another are at what? We already calculated that. Okay, this one, right? These two, these are the 4 poles, open loop poles. So -3 plus minus 2.96. Okay, so this is -3, we have 2.96 j, this is minus j 2.96. These are open loop poles. Okay, so you have to find the angle of departure. So what is this angle of departure? Okay, so until now, okay, let's just recollect whatever we have done till now. Okay, so first we computed the centroid and number of asymptotes. Okay, so how many asymptotes are there? You already see that 4 asymptotes, because there are 4 open loop poles and no 0, so the difference is 4, right? Number of poles minus number of 0 is 4, so you have 4 asymptotes, and these asymptotes angle will be given by this formula, and we find that these are the angles of this asymptote, and we find the centroid, which is just the difference between the pole and 0 values divided by the number of, this is difference a, this difference between the poles and 0, and that gives you this value. So this is the centroid from which you draw these asymptotes. Okay, so and this, okay, so this I will go. So first you see that, okay, these are the open loop poles, right? On the real axis you find that this is only the part where this root locus will lie, because to the right you need odd number of poles. You see that for this one pole is there, right? After this point there is no pole right to this, for this point, and also same for this, in this region. Okay, this region, how many poles are there to the right? 2, right? Real axis, -5 and 0. So it is also not part of the root locus. So only this red color what I was saying, that is the part of root locus, and you see that at this point it will cross this imaginary axis. Okay, 2.84. Okay, so it will be some point here. Yeah, it will cross this imaginary axis, and we already have this green, I mean centroid. We have 2 point something we calculated, right? This one 2.75, and with some angle of this we will draw this asymptotes. Okay, so from -2.75, let it be here, we draw this asymptotes like this, -45 angle, -45, -135 and +35. Okay, now we have to find this root locus part around this asymptote. Okay, so this asymptote means this root locus will be, as k goes to infinity, it will be around this asymptotes. Okay, And we also have calculated the breakaway point, right, for this. Yeah, 1 point, this minus 1.83. So this is some point, yeah, right, 1.83. Some point will be there like this point, where it will break. This, okay. So the angle of departure means, you know, some root locus will start from this point also, right, these two poles. And how this pole will behave near this, how this root locus will behave near this, it may like go like this, this. Okay, so this angle, how it departs from that is called the angle of departure. Okay. So how to calculate this angle of departure? Okay, so
Sir, summation of poles minus summation of zeros divided by asymptote or the centroid value, I guess.
no. Okay, so okay, so you know this pole angles. Okay, so from basic equation. Okay, so you don't have to remember all the roots. You can also find from basic equation also. Okay, so okay, HS I am taking 1. You have this equation, right? So this will give the poles of the system, right? And let write GS equal to this K numerator part by divided by denominator part. Okay. Yeah. So this is the, I am writing GS in terms of numerator and denominator like this. It is given there here. Okay. So then putting this, we have 1 plus K times numerator by denominator equal to 0. Okay. So you see that in the numerator you have this 0 part, open loop zeros, and the denominator you have this open loop zeros. Okay, sorry, open loop poles. And you know that this is equal to GS equal to this, or I can also write GS HS, and I can put here GS HS also. Okay, GS HS equal to 0. This numerator by denominator. Okay, anyway. So then you see that GS HS equal to what? Minus 1, right, from this equation. Or I can also write in complex number, plus minus also I can write 0 like this. And from this angle condition, what will be the angle? 180 degrees, right? It can be plus minus or multiple, because minus 1. Okay, so the minus 1 means what? This line, right? This negative real axis line. And what is this angle? This will be 180. So this is 180. So you see that for this equal to, it should be 180 degree, and for GS HS you see that this are this. So you will take the angle of this, you said angle of the zeros minus angle of the poles, right? Because the poles are in the denominator. So the formula come to it, angle of all zeros angle minus angle of all poles should be plus minus this angle, this one. Okay, so you just apply the same formula everywhere. So for this case, you find these angles. Okay, so I'll draw this here. Okay, so you have a pole at 0, another at minus 5, and 2 complex conjugate poles. Okay, open loop poles, minus 3 plus 2.96. Okay, 96. So it is J. This is minus J 2.96. Okay, so that means your angle of departure means it will depart from this complex conjugate poles from here and here. So you just have to find one part of this root locus, because it is symmetrical about this real axis. So you can draw for other part. Okay, so we just considering upper part only. So we want to find how this root locus branches from this open loop pole will go. It can go like this, it can go like this, we don't know, right? It can go like this also, this. So we have to find how this angle actually formed here. Okay, how this angle is formed. If it go like this, that means this is the angle, how it is departing from this pole. Okay, so this is called the angle of departure. Okay, so how to find this? You know that all this 0 angle minus all the pole angle should be 180 degree, right? Or multiple of 180 degree plus minus 180 degree. Okay, So that means if, let's consider if this point is, okay, this red color dot is in the root locus, that means if I draw this angle from this open loop pole, from this pole, this is the angle, right, of this point, and from this I join this and find this. Okay, so I will use the green color, it will be better to see. Okay, so what is this angle? So if this point, okay, this green color point is in the root locus or not, how to find it? We see that if the angles are drawn, angles of all the line drawn from open loop poles and 0, okay, with this formula 0 minus pole, if they add up to 180 degrees, then that point will be in the root locus, right? So that means I draw one line to this point, this angle, okay, I'll just make it little bit bigger so it will be clear, okay. So let's, this is the point we want to find whether it is on the root locus or not, okay. This point is very near to this pole, okay, I'm just drawing it very far so it will be clear. So what you do, you will join the line and find this angle, so that it will be theta 1, and this angle also you find from this pole. What is the angle of this point? So this is, that it will be theta 2, and this, what will be this point, what angle this, that it will be theta 3, and you have 4 poles, right? So you have to find 4 angles, this one also, the theta 4, okay, there is no 0. So if minus theta 1 minus theta 2 minus theta 3 minus theta 4, so that is minus of this pole angle, right, because there is no 0, minus of this pole angle equal to plus minus 180 degree multiplication 2k plus 1, like, or multiple, then that point will be on the root locus, right? So what we do, we want to find the angle of departure, that means the point should be very close to this point, right, this pole. So for that we can consider this line to be exactly to this pole also, very approximately, and we have to find this angle, right? And then because we don't know this theta 2, how this root locus is going there, so this theta 2 will be unknown there, right? Is it clear?
Sir.
Huh?
Yes, sir, understood, sir.
Yeah, so then you can find this angle of departure, okay. So what you do, okay, I will again draw this. So when this point is very close to this pole, I can take this pole to be this point, right? That means still now we had one pole is there 0, one is minus 5, one is this point, this is minus 3, so you have minus 3 plus z 2.96, another pole is like this here, so minus 3 minus z 2.96, okay. So if a point is very close to this pole, I can consider that point to be very close, means I can also consider this point, exactly that point, okay, because I am considering very close point there. So I will draw these lines all and I will find this angle. So I have denoted this theta 1, and theta 2 is like this point from this close point, what is this angle from this pole, okay. So that we have to find, this is the angle departure. So theta 2 is not known, so this angle I denoted with theta 3, right? And this angle, always this angle are in the counterclockwise direction, okay, in this direction, okay. So that you should remember theta 4. So if I can calculate theta 1, theta 3, theta 4, then I can calculate this theta 2, that is the angle how this point is located, how this angle, okay. So that let's calculate this angle, okay. So what is this theta 4 angle? So you see that this is 0, this is minus 3, and this is 2.96, right? So I can use the tan inverse to calculate this angle, and this will be, then the other angle will be 180 degree minus this angle, right? So first find this angle, let's denote it to be theta prime, okay. So theta prime what? Tan inverse of minus 2.96 by minus 3, right? So I'll just calculate that, tan inverse of 2.96 by 3, okay. So that is some angle 44.61. So because this angle is 44, this angle, okay, theta prime is 44.61, so this angle will be what? Theta 1, theta 4 will be just 180 degree minus this theta prime, okay. So 180 degree minus this This is 135. Okay, so we found theta, this is 4, theta 4 to be 135.38. okay. Similarly, what is this angle? Theta 3. You can directly, you don't have to calculate, right? You can directly see, because these complex conjugate pole are symmetrical located, so this will be just same point, so this will be 90 degrees, right? Theta 3 will be 90 degrees, so minus 90 degrees this term. Is it clear? This is why it is 90 degree, because these poles are symmetrically located, so it is at this point exactly below this, symmetrically to this real axis. So this line will be perpendicular to this line, right? And what is this theta 1? So this is what? Minus 5, minus 3, so the distance is 2, and this height is what? 2.96, same, right? So this will be 10 inverse of that. So 10 inverse of 2.96 by 2, so it is 55, theta 1. So we have minus 55.95, okay, degree, minus theta 2 equal to, you take either positive or negative. I am taking positive 180 degree. So then theta 2 will be what? So this angle, or minus 180 degree, which is coming, okay, just minus 180 degree, minus 55.95, minus 90, minus 135.38. So it is minus 461.33 degree. I can make it positive number by adding 360 degree, okay, because that is same angle, right, after repeating 360. So I will just add 360. So it is minus 101.33 degree. So minus means this angle will be this is 90 degree, means like this angle, okay. This is minus 101.33, because I am measuring in counterclockwise direction. This will be negative number, right? So you see the angle of departure from this pole, this green one I have written, should be minus 101.33 degree, okay. And okay, so let's just draw this root locus for this system, okay, from whatever we have calculated till now, okay. So this is the system of a pole, gain is given GS with unity feedback negative, okay. So we already calculated all this desired quantity, so we just plot this root locus, okay. So these are the open loop poles, okay. One is located at 0, this one 0, one is minus 5, and other two are from this quadratic equation we found to be minus 3, it is J 9.26 minus, this is positive number, this is 2.96, right? These are the open loop poles, okay. Then we calculated this, okay. In the first question we calculated the centroid position, this one minus 2.75, and this asymptote angle, this, okay. So that will be the part of the root locus when k is very large value. So we draw the asymptotes, okay. So I draw with green color. So we have 2.75, this one, from this with 45 degree angle. So approximately I am drawing, okay. So these are the asymptotes, okay. Then also we find this location of this roots on the real axis. So you see that left to this 0 point there are no poles, so it cannot be part of the root locus. Between minus 5 to 0, you see that left right to it one pole is there, 0, so it is part of the root locus, this one. And right left to the minus 5 there are two open loop poles, like in the real axis, minus 5 and 0, so it cannot be part of the root locus, okay. So okay, so this red color is a part of the root locus. Then we find that in this last question this angle is what? Minus 101.33 degree angle of departure from this. So this is something like this angle, So this root locus will come like this from this. Okay, so again I will draw with the red color. Okay, so it will come like this angle minus 100 something will come, right? 101 something minus 101.33 degree. So this root locus, then as it progress, it should be close to this asymptote, right? So it will go like this root locus. And similarly, because it is symmetrical, so for the lower part it will be like this symmetrically. Okay, the angle will be what? 360 degree minus this angle symmetrically, or you can just draw symmetrically around this. Okay, and we also found that there is a breakaway point at minus 1.83, right? So breakaway point means there it should branch from this this one, right? This one between two poles, so it will branch. So it will be some point minus 1.83. It will branch. And where should it go? Because already two asymptotes are covered. These two asymptotes are left, right? This and this. So it will go near this asymptote. So it will be like this. It will close to this asymptote, and this will close, and it will cross at a what point? This imaginary axis we already calculated here, right? Using Raoult-Horich criteria, which is 2.84. So it will be some point here 2.84, and this is some point symmetrical located minus 2.84. It will cross this imaginary axis. So you can see the root locus, this red part is there. From this pole it is going like this asymptote, and this part it will go like this. Okay, so this is the root locus as k value is increased. Okay, if you have MATLAB, you can easily check root locus whether you have drawn correct or not. So the command for the MATLAB is have locus, right? You put this numerator and denominator. So what you do, you put the numerator as a row vector with highest degree coefficient first, then decreasing order, denominator, then you can use MATLAB command to plot this. Okay, to check whether this is correct or not. Okay, just I'm just giving you some way to verify whether you have plotted correctly or not. Okay, anyway, so we'll move to next question then. Okay, so you have an open loop transfer function given here. So here this z is, you can treat z as a parameter here. Okay, this z, and you have to find what is the maximum value of z for which this root locus will lie in the left half plane. Okay, complex plane. So what you will do? Can anyone answer? What should we do now? So first thing is that here you see that it is not k, right? It is not gain, it is just a zero of the system. Z is given, but you can always write it as in k, gain of the system. Okay, then what to do if you can write? So let's do this. Okay, so because you know GH equal to 0, this is the closed loop system, poles will be given by this term, right? 1 plus GH. This is because this is the transfer function, so you just make the denominator equal to 0, which is 1 plus GH equal to 0. So this will give this closed loop poles. Okay, so we will first compute this term. Okay, so we will compute 1 plus GH, okay, and make it to 0. So what is this? You can see that we have to add 1 with this term, so that is SQ plus 4 square. Okay, so square plus 8s plus 10s plus 10z equal to 0, right? From this equal to, that means, okay, I'll just compute it. Okay, so we have 10 into s plus z by s into s square plus 4s plus 8 plus 1. We have to make it to 0. That is the 1 plus gh, this one, right, equal to 0. So we just simplify this. So 10 s plus 10 z plus this is the s cube plus 4 s square plus 8 s by s into s square plus 4 s plus 8 equal to 0. It means the numerator part should be 0, So this is numerator part, this one, s cube plus 4s square plus 18s plus 10z equal to 0, right? Is clear? Now you see that compare this equation with earlier equation we have written for this here. You see that all terms are there and plus k term is there, right? And you can see it is already in this form. Instead of k we have z. So you can still apply root locus formula where, okay, so how to apply this root locus formula for this? Okay, you see that instead of k we have 10z, right? So instead of k, now you again, if you vary this z, which will similarly work as a k, right, in the gain of the system. So you see that you can plot your root locus. So to find, but for this question you have to find at what value it will lie in the left half plane of the complex plane. Okay, so you already know how to find the value of the gain. So here this 10z will behave like a gain. Okay, so for value of the gain, when this root locus will cross this imaginary axis, you already have seen this, right? You have to make a row 0, right? You apply the Routh-Horwitz criteria and make a row 0, where from that you can find for what value of this parameter here it will cross this imaginary axis. So we write the Routh-Horwitz table for this first. Okay, so we have third degree polynomial. So we have S3, S2, S1, S0, S3. Okay, I will write here SQ plus 4s square plus 18s plus 10z equal to 0. Okay, so we have 1. You just complete this Routh table for 10z. Okay, you just write using this. So this will be 4 into 18 minus 10z by 4, and last one will be 10z. So you see that for imaginary axis, what you should do? You should make a row to 0, right? And that will be an odd number row. This one, odd power row. Okay, s to the power 1 is there, so it is a odd power. I mean s to the power odd number is there. So you make this term equal to 0. So you have 4 into 18 minus 10z by 4 equal to 0. That means 4 into 18 minus 10z equal to 0, or z equal to 4 into 18 by, so it is, let's conclude it, 4 into 18 by 10, 7.2, right? You see that at 7.2 it should cross the imaginary axis, right? So it's like this. So it is crossing at the imaginary axis for k value equal to 7.2. So before that the root locus will be in the left hand plane. After that it is crossing this imaginary axis, as you have seen this plot, right? Similar to this plot. At this value it is crossing the imaginary axis. Before this it is in the left hand side of the root locus. Similar to this situation, this root locus plot will be different, but this characteristic will be same, right? So as the value of the k, sorry, here it is z value, not k, z 7.2, then it is crossing this imaginary axis. So that means for value of z less than 7.2, this will be in the left half plane, right? Is it clear? Okay, so you use the same idea, right? So you find the value of the parameter here. So instead of gain we have this 10z. So your analysis will be same, nothing else, because instead of k you have this 10z is there. Okay, you just analyze this using the root locus, and you will find like your variable is what? Here z. Instead of k we have this z variable here. So for what value of z you can make a row to 0, then only this imaginary axis polar possible. So you see that for z value of this you can make this s1 row to be 0. So and we can find like at this point this root locus will be crossing this imaginary axis. Before this value, that is the less than 7.2, it will be in the left hand plane. After like increasing this value beyond 7.2, it will be in the right half plane. So the maximum value will be 7.2, okay, below which the root locus will be in the left hand plane. Beyond this 7.2 value, it will be in the right half, right? Okay. So then next question is again the same transfer function. So how many breakaway and break-in points are there? Okay. So what to do? You just find this dk by ds, right? So instead of the k, here we have z here. So you find the dz by ds and see whether this root locus lies in the, this breakaway points lie in the root locus or not. If it lies in the root locus for some, that means also the k value is positive, then it is a breakaway or break-in point. Otherwise it is not, right? So okay, so just we'll do this problem also. So we already have this characteristic equation. Okay, so we already written here, right? What, this one. So we will write z in term of s. Okay, so I'll just write this. Okay, so we have a sq plus 4 square. I'm just writing this equation again. 18s 10z, okay, plus 18s plus 10z equal to 0. That means z equal to what? Minus 1 by 10 sq plus 4 square plus 18s. Okay, we take the derivative now, dz by ds. So it will be equal to what? Minus 1 by 10 3 square plus 8s plus 18, and make it equal to 0, dz by ds. So equal to 0. That means you have to solve for this, for s value. Okay, so if you solve for this, you will get roots. Okay, you can use calculator to solve this. So these are the roots, complex conjugate root. Okay, something 548. Okay, plus minus. Okay, for this characteristic equation equal to 0, you see that these are the complex conjugate values, and see whether they are located on the root locus or not. Okay, so to do so, first we will roughly draw this root locus for this. Okay, so okay, so for this this is the characteristic equation, s square plus 4s square plus 18s. Okay, because this is the k value, so this will be the characteristic equation, just excluding that z value. So you calculate the root of this. So 1 is z is 0. So okay, I will write this here. So here, okay, so one caution what will be, this is not like you don't solve this to find this open loop poles. Okay, so can anyone say why should not we solve this one? Okay, so because in the standard form it will be given like this. Okay, you have some zeros or not and poles are there, right? The k should be the multiplying term. Here you see that this z is a parameter that is not multiplying like this. Okay, so you have to find a form of this where this is multiplying like this, right? So you have a form like this, z into some term by this. Okay, so you can easily see, okay, from this characteristic equation, this one. Okay, you just verify this. If I take g dash, okay, g dash is just, okay, instead of this, as this form 10z by s cube plus 4 s square plus 18s, then 1 plus g dash, this will be the closed loop poles, right? And this will be similar to this equation, same is equation. And you see that this z is like a gain here, k. And how I find this? You see that these are this term, right, up to this, excluding this term, I find that s cube plus 4s plus 18s. Okay, and why I have taken this, as you can see, Okay, we already have this form, right? So this k value excluding that other terms will be this one in the denominator term, right? So from this you can guess what should be in the denominator term, and you can find this poles from this equation. Now is it clear why we are taking this term instead of this term, right? This will be what, if I multiply this and expand it, it will be s cube plus 4s square plus 8s, right? I am not solving this to find the open loop poles. I am solving this one. You can see the difference, it is 18s there, okay, instead of 8s. That is coming from this term, okay. Is it clear why I am solving this to find the open loop poles and not this?
Sir, can you repeat once again, sir?
Yeah, sure, yeah. Okay, so let's, okay, right. Okay, so in the standard form, okay, when you plot the root locus, how this gain appear? Okay, I will go to the standard form, already we have done, right? Here you see, right, here how this gain is appearing here. It is appearing separately. You can have zeros also, right? S plus some z or something, but it is appearing as a multiplying term, right? It is not appearing inside this term, s term, right? Like when you apply this root locus technique, okay, so this k is a multiplying term, right? It can have zeros also. For this example, it can have like s plus 2, s plus 3, like these zeros, but it always is a multiplying term to these factors, right? This is the gain. When you vary this gain, you plot the root locus, right? Is it clear?
Yes, sir.
Yeah, but for this question that we are solving, you see what is this parameter now? Z is a parameter, right?
Yeah.
And z is not
Yes, sir.
in this form, right? It's not multiplying there. It is actually inside this term. It is zero because it is a zero term, and we are varying that zero. So what we do? We transform into the standard form. This form, right? Where it is a gain. This z will appear as a gain, so it will transform like a z term some zeros, okay, by divided by this poles term. Then only we can find this open loop poles and zero, right?
Got it, sir. Got it.
Yeah,
Yes, sir.
yeah. So because here we are treating z as a parameter, so this z should appear as a gain there, not as a zero, like this we have here. So what we will do? We will write the characteristic equation first, closed loop system equation, which will be 1 plus gh, right, equal to 0, and that term we found here. This is this equation, closed loop characteristic equation, okay. Now using this, can you write in this form, standard form? You see that if you take this is a gain and this is a denominator, then we can have this one, right? If I take like this, then z by s cube plus 4s square plus 18s, right? If I take gs hs equal to this term, then 1 plus gs hs will be what? This will be, right, in the numerator part. Okay, I will just write, okay, it will be clear then. Okay, so you have this closed loop equation, right? Closed loop pole equation. Up to this it is clear, right?
Yes, sir.
So from this we will write in a standard form like this, where this gain will be a multiplying term, okay. Instead of instead of like this here z, it will be z should be some multiplying term. So what we will do? We have this characteristic equation there. Where is it? This one. This is the characteristic equation, right? Yeah. This is the characteristic equation we found, or here. This is the characteristic equation we found it, okay. From which we will write GHHS form, okay. So it should be what? It should be the numerator of this, okay. Let denote it to GH prime, this new transfer one. It should come with this term, right? From this we will find this. You see that this means, okay. Okay, let's g prime h prime to be this z multiplied with some term divided by this coefficient. We want like this form. Okay, so what I will do, I will write it n, I will denote this numerator n and the denominator d. Okay, so then 1 plus g prime h prime will be what? You see that d plus z numerator should be equal to 0, right? This one. Is it clear?
Yes, sir.
Because we are equating the numerator to 0. The numerator part will be what? If I add 1 here, okay, so this is 1 plus this, so I have 1, so this will be what? Zn plus by d, and if I equal to 0, that means this numerator part should be 0, that means this term should be 0. Okay, now compare this term with this term. You see, what should be the n value then? That is multiplied with z, right? 10, right? And what should be d? That is separated from this term, right? This one, s cube plus 4s square plus 18s, right?
Yes, sir. Understood, sir.
Yeah, so instead of doing all these things, you can like guess also, right? I'm just doing this to explain this. You can guess that this term, okay, this 10z term will be this gain term, that is in the numerator part, and the rest of term will be in the denominator part. That is what we did there. So this is the form for which this z will appear as a gain. Okay, so for this, then we will find this open loop poles from this equation. So open loop, to find this open loop poles, we have to solve this equation, s cube plus 4s square plus 18s. Okay, so compare this with the whatever given there. Here it was actually 8s was there, not 18s. Okay, so how this 10 come, 8 plus 10 come, you can see this above term actually coming there, right? So what we have essentially done this, because in the numerator part we have 10s plus 10z, right? So this done, because this anyway when you write 1 plus hs, this term will add up, right? So that term is coming with 8s here, as you can see 18s. So then we have only 10z is left, which is in the numerator, as you can see 10z. Okay, so then only we have a term which is actually as a gain there. So that you can see that the 10s is actually added with this 8s. Then we have a standard form there. Okay, so from which also you can verify whether you have done correctly or not. Okay, so then you have to solve this equation to find the open loop pole, or that is also equal to what? S times s square plus 4s plus 18. Okay, and the solution of this, okay, I am using calculator to calculate this solution. Okay, so quadratic equation we have 1, 4, 18. Okay, so we have complex conjugate poles. Okay, so I will write here space. Okay, I will just remove this. Okay, so these poles are at -2 plus minus j 3.74. Okay, and 1 is at 0, right? 1 is at 0, and this quadratic from we got this pole. So these are the poles. So roughly, if I want to draw this root locus, so one is located here and other are located like this. Okay, and you see that for the standard form there are no zero, right? Finite zeros in the standard form. The z is again, so there will be 3 asymptotes, and this asymptote you can easily guess what will be the angle. -60, 180, -60°, right? Like this. And what should be the asymptote value centered? Can you directly say from this equation what should be the value of the centered? All the poles. Okay, so poles centered calculation, summation of the poles minus summation of the zeros by difference between the pole number minus zero number, right? So here there is no zero, there are no zero, right, in the standard form. 10z is there, and 3 poles are there, and the poles are located at 0, -2, -2. So the summation is -2, -2, -4 by 3. Okay, and you can easily see from this also without calculating this. So 1 is located at the 0, this pole, and the summation of 2 pole is what? This term, right? Because the complex conjugate term will cancel out. You can see -2, -2 is 4 there, minus of -4. Okay, because this will cancel out. Because why? Okay, so when you write like this, okay, a square plus a plus b s plus ab, right? You see the summation of the poles will be coefficient of s in the quadratic, right? So the summation of the pole will be means negative of, because the poles are at -a -b, so a plus b means negative of this term will be the sum of the poles, so it will be -4, right? I mean, you can directly guess also, you don't have to calculate this. Okay, if you think this is complicated, then you just apply the rule directly also. So summation of the poles will be what? This is -2, -2, -4. This imaginary term will cancel out, plus 0 by 3, because there are 3 poles are there, no 0. So here -4 by 3, which is what value? -4 by 3, so it is 1.33, right? So let's draw here. Okay, space. Okay, I will draw here. Okay. So we have 1 is located at 0, other poles are -2, this term. So these are the poles, and this angle will be what? 60 degree, and from center we have calculated -1.33. So this is -1.33, right? So one centered will be this one, and this one. Okay, so if you see this will be the root locus part, right? Because to right of this one pole is there, you see this one, and other two will go like this. Okay, roughly I'm just saying, because I have not calculated the angle of departure, so this angle you have to calculate. But you see that there are no breakaway or break-in point are there, right? So you see that no breakaway break-in point are there. The breakaway break-in point only happens if there is a part of the root locus between two poles, okay, like this, then there will be a breakaway point, the poles will break. Or it is between two zeros, then there should be some break-in point. That means this root locus will go this turn and then will move. Okay, but this situation does not appear here in this plot. Okay, so there is no breakaway break-in point. Okay, or you can also, by calculating this, you can verify that this value of the imaginary value actually does not satisfy your magnitude condition. That means your k cannot be positive number for this. So from this also you can verify. Okay. Okay. So the next question is, okay, so you have a upper loop transfer function is given. Okay. Now you see that k is varying from 0 to -infinity. Instead earlier we have positive gain, here we have negative gain. So this is a positive gain transfer function, right? You need you have, is it clear why it is positive? Because okay, for negative feedback system you vary this k from 0 to infinity, right? For negative gain, if you take this k to be, okay, negative number, then you see that instead of k I can write k dash. Okay, I am taking k dash to be positive number. Then you see that it will be 1 minus gh, right? So you have a positive feedback system. Okay, is it clear why it is a positive feedback system? When k is varying, k value is in a negative range, you see that this will be negative term, right? So I take k prime to be minus of k. Okay, then if k is from 0 to -infinity, k prime will be what? 0 to infinity, right? It will vary. So I will write,
Yes, sir.
yeah, so I will write it as a minus k dash s plus 2 by s plus 1 s plus 3. Okay, so now I take without this minus sign, okay, I take it to be some g prime h prime, okay, the term. So you see that 1 plus g prime h prime, instead of that, if I write it as an minus term, so I will get back to this form, okay, because minus k, I can write minus k prime s plus 2 by s plus 1 s plus 3, right? I have taken this to be this term, so but minus k is what? K, right? So I will get 1 plus k s plus 2 by s plus 1 s plus 3. So you see that this term I can also for this it should be the closed loop poles, right? That can be written like this, 1 minus g prime h prime, where g prime h prime has positive gain k, right? So you see that it can also be considered as a negative positive feedback system when the k is varied in the 0 to minus infinity, okay. So for this, okay, so which this is also called complementary root locus when this gain is varied as a negative, okay. For this, what part of, okay, I'm not writing it, what part is actually on the root locus, okay. So let's see. So now we have negative gain means we have like this system, right? Sorry, positive feedback system means like this, right? So GH is equal to 1, right? So angle of what? It will be what? Either 0 degree. I can also write this like this, right? 0. So the angle of this is what? Positive 1 means this, right? This is either 0 or 360 degree I can consider. So earlier for negative feedback system we have 180 degree, right? Plus minus 180 degree. Here we have 0 or 360 degree. So that is the angle criterion has to be modified. So that means, okay, for real axis, okay, so for negative feedback, what do you do? Okay, if there are pole, you see that for this part, if there are odd number of poles are there on the right hand plane, right hand side, for this you have one pole here, right? So it will be part of the root locus, because from this angle will be 180 degree, right? And if there are like 3 are there, you see that 180 degree from this it will be 180 degree, 1 point I'm considering, from this also 180 degree, and from this also 180 degree. So if there are odd number of poles are there in the right hand side of this point, you see that we are multiplying a odd number, okay. If m is odd, because each pole will contribute 180 degree, right? So m will be odd, and you are back to your original condition, that is 180 degree or multiple angle is there, right? So this condition is translated into what? Or simply putting, if for a point, if odd number of poles are there for negative feedback, then that part will be root locus part. If even number of poles are there, that part will not be part of root locus for negative feedback system. So for positive feedback system, what will happen? You need 0 degree or 360 degree, right? So that means even number of poles are there, because 180 degree, if it is multiplied with even number, it will be multiple of 360 degree, or that can also be considered as 0 degree, because 360 degree means this one, right? Angle. So this is also 0 degree. So the rule will be modified. So a part of the real axis will be part of the root locus for this positive feedback, or when this gain is very negative, only part it will be part of the root locus only when even number of poles are located on the right hand side of this position, okay. So what that means? So first find this 0 and poles of this open loop transfer function. So 1 is at minus 1, this is minus 1, that one pole is there, and minus 3, another pole is there, and 0, 1 0 is there, right? So this is minus 2, so this is 0, okay. So now you see that what part are actually part of this complementary root locus. I am denoting the green. For this part, you see that there are no pole or zero to the right of this. So even number of zeros or poles. Zero means even number also, right? This is the part of the root locus. The real axis part I am just drawing. Okay. For this position, you see that one pole is there. So for this you need even number, right? For this complementary part. So this is not a part of root locus. This is part of the root locus. For 2, 1 0 and 1 pole, that is the even number of open loop poles or zero are there. And again this is not part of root locus. Okay, so you see that this is part of, this is green part of. Okay, you see that then what point can lies on the root locus? Minus 4 means this point, so it cannot lie. Okay, and minus 2.5 means this, so it can lie. Okay, but it is wrong. Then again minus 1.5 will be point somewhere between these, it cannot lie. 0, okay, it is lying. Minus 1.5 will be some point between this, so it is lying. Sorry, minus 1.5 is not there, right, between this, because the part is there. This is not. Minus 2.5 some point between this, and 0, you see that 0 point is minus 2.5 is there, some point here. These are part of the root locus, so D is the correct answer, right? Is it clear? So check the complementary root locus, or when this gain is negative. Okay, you can see like how to find this. So some rule will be modified. This angle condition will be 360 degree. Okay. Yeah. So is it clear? So check this, when the gain is negative, how to find this root locus. So some rule will be modified. Instead of 180 degree angle, it will be 360 degree. Okay, and almost all rules are same. You can check this. Okay. So the next question you consider. So you are given characteristic polynomial. Okay, so you are given characteristic polynomial. So which of the statements are true? Okay, so for this, let's just draw this root locus first. Okay, we can directly draw this root locus. So this SQ plus 15 S square plus 54S plus K. So how to find this open loop poles of this system and zeros? You see that this term will be coming from, okay, if you remember, denominator plus K into numerator equal to 0, right? Numerator is what? 1 here only. Denominator part is this one, D. Okay, when we make 1 plus GH equal to 0, and if I take GH to be like K numerator by denominator like this, then you see that D plus Kn by D equal to 0, that means D plus Kn equal to 0. So this is what given here. So the comparing with that, numerator part will be 1 and denominator part will be the rest equation without K. Okay, so to find the open loop 0, there is no 0. Open loop poles will be solving this equation. SQ means I can take S common, so S square plus 15S plus 54 equal to 0. That means S1 is solution 0, 1 will be S equal to minus 6 and S equal to minus 9. These are the open loop poles and no zeros are there. Okay, so then we'll draw here. Okay, the root locus. Okay, so we find 0, minus 6, minus 9 are the open loop poles. Okay, so minus 6 somewhere here, minus 9 here. Okay, then part of the real axis, that is actually part of the root locus. You see that this part will be, because odd number of poles are there to the right, and this part will be part of the root locus. Okay, then asymptote, how many asymptote will be there? Because 3 poles, no 0, 3 asymptotes, and the angle you can easily guess, 60 degree, 180 degree, minus 60 degree, right? And what is the centered value? Sum of this poles, 6 plus 9, 15 by 3, 5. So at minus 5 will be asymptote, 1 will be 60 degree, and green, minus 60 degree and 180 degree, this one, right? Okay, So these are the asymptotes. Then you see that you have to find the j omega axis crossing point. Again you apply the Raoult-Horowitz criteria to find this. So I just write it quickly. S square, S1, S0, so 1, 54, 15, K, right? So it will be 15, 54 minus K by 15 and K, so K should be positive and K value should be this one, and K will be then what? 15, 54 into this one, right? 54 into 15, so 810. So from this you can find this one, the Quetelet equation, that is 15 S square plus K 810 equal to 0, means S equal to what? Square root of this, so 810 by 15. Okay, so S is equal to plus minus J square root of 810 by 15, which is plus minus 7.3435. Okay, so at 7.35 it will cross. Let the point be here, J 7.35 and some point minus 7.35. Okay, you have to find also breakaway point. So to find this, we take K equal to what? This equal to 0 means K equal to minus of S cube plus 15 S square plus 54 S. Okay, so dk by ds equal to what? Minus of 3 S square plus 30 S plus 54. Okay, so you equate this 0. So from that I'll just solve it using calculator again. So 3, 30, 54. Okay, so one is at solution is minus 2.35, another is minus 7.6465. Okay, so you see which of the point lies in the root locus. Okay, one is minus 2 point something and one is minus 7.65. Okay, minus 7.6 point will be some point here which is not in the part of the root locus, so it is not a breakaway point. Okay, minus 2.35 actually lies, so let it be some point here. Okay, minus 2.35, so it will break here. Okay, like this, and you go. So this is the root locus. Okay, we have drawn almost roughly we have drawn. So let's just check this point. So the roots of the all real roots are all real for all positive value of K. Okay, you see that roots can also be complex conjugate, right? For this region it's not real. So the first statement is false. The roots lie in the left half plane of the complex plane for all positive value of the K. You see that it is actually crossing the imaginary axis and going to the right half side of the. So the second statement is also not true. If the root exists in the right half of the complex plane, then they are not real. Okay, you see that in the right half plane the roots are only imaginary, right? A complex plane, it are not real. These are complex number, not in the real axis. Okay, so this statement is true. The root locus has a breakaway point between minus 6 and 0. We already calculated minus 6 and 0, there is a breakaway point, so it is also true, right? So 3 and 4 are true. Okay. Okay, so we'll do last question then. Okay, so you have a open loop transfer function again given in this form, and alpha is the parameter here, and alpha positive number, so we are varying alpha between 0 to infinity and finding the root locus. So you have to find the breakaway point and imaginary axis crossing point. Again you just apply the standard rule, but for that you need it to be standard form. So this is equal to, I can write 2s plus 2 alpha, this is s square plus 2s into s plus 10, so it will be s cube plus 10 s square plus 2 s square plus 20s, right? So it will be s cube plus 12 s square plus 20s. Okay, so the closed loop equation will be what? I just add this 1 because GS HS is given as 1 unity feedback. So I have the closed loop equation to be s cube plus 12 s square from this plus 20s plus 2s, this term, plus 2 alpha equal to 0. So we have s cube plus 12s square plus 22s plus 2 alpha equal to 0. Now you see that what will be in standard form, what will be? It will be 2 alpha, this is will be in the above, this will be denominator part, right, in the standard form, 22s. Okay, so this is the equation. Okay, or because we want to find this, we don't need also this form, because we want to find this breakaway point and the imaginary axis crossing point. So I will write, instead of the k we have alpha, so we write alpha equal to what, minus half time s cube plus 22s, right. So I'll take d alpha by ds and I make it 0 to find breakaway point. So from this it will be minus half 3 s square plus 24s plus 22. Okay, so I will solve this again using calculator. I am solving it. 3 24 22. So one point is minus 1.056 5 and another is minus 6.943. Okay, now we need also we need to verify whether these 2 points, out of which point actually lies in the root locus. Okay, we will do that here. So we will roughly just plot the root locus also. Okay, so this will be the part. Okay, in the numerator denominator part it will be like this in standard form, right, s square plus 22s, and this is from which I can take common and I can take 12s plus 22. So one is at 0, another polar actually, again I am solving using calculator. I can solve it to 12 and 22. So this is one is 0, poles are 0, another is minus 2.258 and another minus 9.74. Okay, so that means one is it is 0, one is minus 2 point something, so minus 2.258, another it is minus 9.74. So this is part of the root locus, because odd number of poles are in the right part. This is also part of the root locus. Okay, so you see that minus first point is on the root locus part, a second point is this one, minus 6 point something, is not, it will be somewhere here in this, it is not in the root locus part. So this is only the breakaway point, right, first term, second term is not. Okay, so you see that only these 2 out of option will be true. So we'll just verify at what point this is actually crossing this imaginary axis. So to do that we will use Rao-Thoris criteria again. Okay, so again straightforward. Okay, so we have, this is the closed loop equation, this one I write again here, s cube plus 12s square plus 22s plus 2 alpha. So I will construct the Rao-Thoris table, s cube 2 s1 s0 1 22 12 2 alpha. So you have 12 22 minus 2 alpha by 12 and 2 alpha. So one condition is alpha should be this, which is already given, and then to make it the row 0 we have to make this equal to 0. So from which alpha will be equal to 12 into 22 by 2, right. So it is 12 into 22 by 2, 132. Okay, 132. So then the auxiliary polynomial will be what? From this it will be 12 s square, 2 alpha means 2 times 132 equal to 0, or s equal to plus minus j square root of 2 into 132 by 12, which is equal to 2 into 132 by 12. Okay, it is plus minus j 4.6 6 9. Okay, so this is the point at which it will cross the imaginary axis, some point here. This is 4.69. Okay, and roughly you can draw this root locus like this also, because the asymptote will be 60 degree. So we already found this is the breakaway point, so 1 point something. So the root locus will go like this. Okay, this is point passing, and this is the. So you see that one is this one and this one. So B is the correct answer, right? This is the imaginary axis crossing point, and this is the breakaway point. Okay. So the idea is just transfer into standard form, and then you apply the standard rules, right? You know the rules. So first you have to write it in the standard form, where this parameter that you are varying should be as a multiplying term, like the gain term. Okay. So that's all. Okay, so any question? Okay, I just rushed because this is standard step, right? Once you write it as a standard form. Is it clear? You have doubt?
No, sir. Like we have to practice once, I guess.
Yeah, you can practice, because there will be some you can do mistakes, so do lot of practice, then it will be clear. Okay, so go through like standard example and see, because you can go through some book example and practice whether you are getting the same thing, and you can also verify using MATLAB. Okay, you can check how to plot using MATLAB. If you have MATLAB, you can use MATLAB to plot, and then also verify whether you have gotten a correct right plot or not. Okay, so try. If you still have question, you can ask. Okay, later also you can ask. Okay, so okay, then we'll stop. Okay, we'll meet next Monday. Okay, just try some examples there and see, because there are some rules you have to practice them. Okay, so we'll stop.